41 billion tons is being emitted globally, and because of this, roughly around 2 to 3 ppm of CO2 concentration increases on average every year. Currently, we are roughly 425. Now, if you do some maths, you will figure out that in next 5-6 years, we will emit another 250 billion tons of CO2, and that means that there will be a 50% chance that we will go above 1.5 degrees what was present before the pre-industrial time. So it basically means that unfortunately this is a bus which we have already missed. In next 5 years, I am not sure we can do anything. Now let's talk about this, which is a bigger, little easier to tackle, that is 2-degree rise in global temperature compared to pre-industrial times. Now in this particular case, there is almost 1150 billion tons credit we have, which we can emit. And the day you emit more than 1150 billion tons of CO2 into the atmosphere, this is the day when typically, I'm just trying to say it's not a hard rule, but you will go beyond that 2 degrees. Now the question is that, should we emit it in next 10 years, 20 years, 30 years, or we should never emit this? If we are not able to achieve this target, it basically means we are going to breach this number of 2 degrees also. And then we will have to have another target that by 2100 we will become 2.5 degrees or so. So that's the challenge going to be. Now, don't want to go too much of detail, but if some calculation says that in next 20 years roughly, we will have to cut down CO2 emission by 700 billion tons. 700 billion tons in 20 years. Let's say we will cut down 500 billion tons in 20 years. Even if we do that, it basically means that every year there has to be significant cut of CO2 which is needed. Okay? Now, where the cut is going to come from? These are the sectors we typically emit CO2. And what I am trying to point out over here, that there is no one solution which fits all these sectors. Depending upon which sector you are, for example, in transportation sector, you can't do a CCUS. Carbon dioxide capture, utilization, and sequestration kind of process cannot be done in CCUS in transportation, because you are talking about an on-board application. Okay, you remember we have been able to achieve little bit of success in cutting down our emissions from the tailpipe. But these are just emissions, 400 ppm, 500 ppm maximum in ppm level. CO2 is the main product of the, when a car runs, CO2 is one of the main product. Energy is a product which we use, but the CO2 is the main product. You can't say that I'll capture the entire CO2 from the tailpipe of a car. It's not possible. So in this particular case, you will have to rely on fuel switching, you'll have to rely on using renewable, and you'll have to rely on increasing energy efficiency. Similarly, other industries will have different solutions, and the biggest power, CO2 emitting industry, that is power sector, has to most probably go into renewables. This is one of the best approach. And then still there will be significant amount of CCUS or CCS which has to be done. CCUS is carbon dioxide capture, utilization, and sequestration. CCS is carbon dioxide capture and sequestration. We will talk about it. The point I was trying to make, that it's a significant large amount of CO2 emission which has to be cut down. And the two simple solutions which has been talked about is moving to renewable and doing carbon dioxide capture and sequestration, or carbon dioxide capture and utilization. Now let's try to understand how we have been doing it when it comes to renewable energy. The story for India is this. We had roughly 25% plus green energy in 1985. Today we are lower than that. We have only 20%. So what it means is that it's not easy to move from fossil fuel based economy to renewable economy. It's very difficult. There are challenges. The people have been trying, but the data clearly shows that there has been some challenges. And actually it was going down till 2005, and from there it has stabilized. And due to the solar revolution a bit, you see there has been significant uptick in recent times. And I hope this keeps going up. But even in next 10 years, we are not going to go beyond 1985 what we had. So this is one of the challenge, and this is because of our huge use of fossil fuels for our growth. You see the CO2 emission in India is almost now asymptotic to the y-axis. We are roughly 3 billion tons every year. Again, the number is 3 billion tons every year, and in India it is increasing by 5% every year. So it basically means that in next 10 years, if you don't do anything, we will become the second largest CO2 emitter in the world. We will roughly be 6 billion tons. Now this is a challenge. And this is the challenge. So renewable, let's try to understand. People say that we will go to renewable and this problem will be solved. I'm sure it will be solved, but it's not that simple. Talk about solar panel, it requires huge amount of material. Today I am going to formulate the problem. See, one of the problem is this. If I am going to use fossil fuels to produce 1 terawatt hour of electricity, you see only 1,000 tons of material has to be moved or processed. Because this fuel has been created over millions of years. All the CO2 which was supposed to get emitted during the processing of this biomass, which converts that biomass into fuel, has already been emitted. So you are not adding any carbon dioxide to the mix while you are processing this fuel, when you are getting the fuel. The CO2 only comes out when the fuel burns. Okay? And this is the reason why when you are producing 1 terawatt of electricity, the material which you are going to move is not going to be significant. It's already cooked for millions of years. You are just taking that cooked material and you are eating. That's all. But the CO2 comes out because of the process of combustion. So you see the material consumed here is significantly lower than the material which you are going to consume when you are going to install a new facility of renewable energy. Now renewable energy materials are being produced today. It's not there from last 20 years or last 1 million years. These are the materials which are being produced today by consuming the same fossil fuel. 99% of this material being produced today consumes the same fossil fuel, which basically produces carbon dioxide. Okay, so now let me tell you solar data over here. So for 1 terawatt hour, I need roughly 16,000 to 17,000 material processing. Now for steel industry, roughly 1 kg of steel billets when you produce, just for the process of steel billet production, 1 kg of billet will emit roughly 3 kgs of carbon dioxide. I am not even talking about the mining, the transportation, the processing of this billet into metal sheets, and then giving different properties to this metal sheet. So let's say in a single step, I am producing 3 kg of carbon dioxide for every kilogram of material which I am producing. Now let's try to understand how much carbon dioxide I have already produced when I am trying to produce this solar panel. Now the next challenge is, solar panel unfortunately has a very poor plant load factor, okay? Because you will have to install at least 4 times than what it is required for the entire day of your electricity use, because sunshine is only for 6 hours. So it basically means my installation has to be 4 times, 5 times of this amount. So it basically means 50,000 tons of material for 1 terawatt hour of electricity. Now that is producing the electricity. How you are going to store the electricity, that adds further to this CO2 emission. So it's important for us to understand that we are talking about net zero. Today, if I am installing a solar power plant or solar plant, it does not mean that from tomorrow you are becoming net zero. You have already emitted carbon dioxide for next 7-8 years. That is something which you will have to always keep in mind. You will become net zero, no doubt about it. It's always better than fossil fuel, but it's not today which you are becoming net zero. And this is the reason why you see world over the CO2 emission is keep going up and up, even though we are moving from non-renewable like fossil fuel to renewable resources. Because the CO2 emission is coming up, these are the new material which are being produced today. If I don't do this, the only CO2 which will come out from the existing plants. But these are the new materials for which we are, obviously our GDP is increasing, but our sustainability is in question mark. Anyway, moving on, the storage of this electricity. How do you store this electricity? Don't want to talk about batteries. I'm sure all of you know what are the challenges with batteries storage and all. I hope there will be a step change technology and tomorrow a small amount of material will be able to store a lot of electricity. Today it's not the case. I'm skipping that discussion. But people keep talking about we'll go hydrogen, green hydrogen. Let's try to understand the maths for hydrogen. Okay, if I'm going to produce electricity from solar and I am converting that to hydrogen so that I am able to store that excess electricity as hydrogen, 55 units of electricity will produce 1 kilogram of hydrogen. It could be 50, but the numbers are around the same ballpark. Okay, now even for 100 to 300 meters of transportation of this hydrogen, I'm not talking about 1,000 kilometers transportation. 100, 200, 500 meters of transportation from the site where you are producing from some other site where you are going to store, you will consume another 10 units of electricity. So it basically means 60 units of electricity you are consuming for producing 1 kg of hydrogen. Now today this electricity is coming from the same grid. Unfortunately, we will be able to do this electricity I am trying to say. So 1 kg of hydrogen will now produce only around 15 to 20 kilowatt of electricity. Again, if you see the plant load factor, I have added 60, 70. How much I am getting? 15, 20. So this is another efficiency loss. This is for hydrogen. Similar number will be there for batteries. And these are supposed to store for the remaining 16 hours of the day. So it's going to be substantial. So it's again not true that hydrogen, green hydrogen will be having 0 CO2 footprint. Look at the electrolyzers and all which will be required. The physical footprint, the CO2 footprint is not going to be 0 for all of these. These are the story of renewable energy. I am not saying that this cannot be done. Certainly these are net zero processes, but it will take you 7, 8 years, and don't change your panel every 8 years in the name of efficiency. Otherwise you are going to negate all those effects of net zero. 7, 8 years down the line, if someone tells you, I have a panel which will give you better efficiency, let's change it, you have done all the hard work is gone to the drain. Because then you will rebuild the entire process. Maybe the CO2 footprint at that time will be slightly lower than what it is today, but there will again be some CO2 footprint for next 4 or 5 years. So be careful with that. Now let's come to, I think I'm running out of time. I'll come to the CCUS, again the formulation definition over here. What is net zero? People say we will do carbon dioxide capture and utilize it. Let me tell you, we are talking about net zero CO2. What is net zero? The carbon dioxide which is captured either from the air or from the point source. 1 molecule of CO2 if I am capturing, the capture process, the transportation process, or the sequestration process, or the capture process and conversion process should emit less than 1 molecule of CO2. Then you are net zero. Otherwise, you are net positive, and let me tell you, none of the current processes are net zero. None of the current processes are net zero. You do a proper counting. It's true that we have to do R&D. We will keep moving in the right direction. But today, it's not net zero when you're using fossil fuel to capture the carbon dioxide. There is a huge amount of penalty, not in terms of energy. Most of the people calculate it in terms of energy. See, the problem here is it's not the economics we are trying to solve. It's not the energy problem we are trying to solve. What we are trying to solve, this is something which should always, one should keep in mind. We are trying to solve net zero problem, that there is 1 molecule of CO2 which are being emitted. Has to be, some process has to be there which will keep it below 1 molecule to the atmosphere. So this is something which you always keep in mind. These conversion processes require significantly large amount of hydrogen. And I just showed you that hydrogen itself is not net zero. The cost certainly comes into picture, which I am not going to talk today. But the point, the formulations which I was trying to tell is that these are the processes which are currently available. I am not saying that these are not going to work. What I am trying to say, please, whenever you suggest a process, please do the right calculation. I want to just show you 2 more slides. This is the slide which is darling of industry that we will do through amines. Now let me show you what is the challenge. This is the amine which you say that I am going to use. Is this going to come from thin air? We have to produce that amine. Where it will be produced from? We need ammonia. Are we producing it from green ammonia today? We are not. Green ammonia requires green hydrogen. So now we need to produce ethylene oxide. Today the only source of ethylene oxide is fossil fuel. There is no other source of ethylene oxide today. So when we are saying that we will produce this and will become CO2 neutral, you have to be very careful with these kind of numbers. This will have its own CO2 footprint, this will have its own CO2 footprint, and then you will have to first capture all the CO2 which is coming in this process. And once we do that, then I have to capture this CO2. It requires you to do multiple cycles. So regeneration has to be the question rather than my material captures little more CO2. Not going to solve that problem unless and until you are able to regenerate 10,000 times. Then only you will become net zero. So these are the problem formulations I was trying to say that, okay, today we will focus on this. And I'll show you one of the most celebrated unit. This is the unit which you would have heard about in Iceland, Orca. Okay, what is this unit about? It captures carbon dioxide directly from the air. How much carbon dioxide it captures? 4,000 tons in a year. How much? 4,000 tons in a year. Look at the physical structure. How much CO2 it has emitted while this physical structure was put in place. Look the physical footprint, the amount of space which it is covering. It has already emitted for next 10 years. It's not that it is good, bad. It is better than planting a tree actually, because in this space, if I am going to plant the tree, it will be less than 4,000 tons per year. But this is not how we calculate. You will have to calculate in a many different ways. I am not going to talk about today. But then this is a solution which is touted solution. Today it may not work, but tomorrow it may work when we are going to do this all through solar energy. Not for today though. That's all from me. We have done similar solutions in our lab. You can come to IITM. You see, we have done direct air capture also. I am not claiming that my processes are better than someone else's process. We are exactly as poor as you could be. Don't worry about that. We are trying to work on it. That's all. So thank you.